We will go over work and work energy theorem in this video. So let's start with work done by a constant force. So if you have a force acting on an object and it moves for displacement s, and the angle between your force and your displacement is theta, then the work done by this force can be calculated as Fs cosine theta. So you see, work done by a force depends on three quantities. First, the magnitude of the force. Second, whether there is displacement. Third, which is also very important, is the angle between the force and the displacement. The force and the displacement. So because of this cosine theta, you see, if the force is in the same direction of displacement, if say F is in the same direction of S, then the angle between them is 0. We have cosine 0 degree equals to 1. If the force is perpendicular to the displacement, you have the angle between them is 90 degree, cosine 90 degree gives us 0. So the force perpendicular to the displacement is not going to do any work. On the other hand, if the force is in the opposite direction of displacement, then the angle between them is actually 180 degree. So cosine 180 degree gives us -1. So this force, which is opposite to the direction of displacement, is doing negative work. Now let's look at the heavy weight lift, for example. So the lifter is always apply force up. So the force is always up when he is doing lifting. So when he pushes the weight up, the displacement is pointing up. You see, force pointing up, displacement pointing up. So he's doing positive work to the weight. During the process, he lowered down the weight. He still needs to apply a force. Let's only think about the force applied by the lifter. Thus the force applied by the lifter is pointing up. Displacement is pointing down. So displacement, so the angle between them is 180 degrees. So in this case, it's doing negative work. When he pushes it up, it's positive work. Lowering the weight, negative work. Now we define the kinetic energy of an object, 1/2 mv squared. And then we can check the unit for kinetic energy is the same as work. So that should be the unit for work, because work is force times displacement times cosine theta. Cosine theta, there's no dimension, no unit. And F unit is Newton. So for work, its unit is 1 Newton times 1 meter. And I will give it a special name in joules. Now, what is SI unit of kinetic energy? 1/2 mv squared. So you see its unit is unit for mass, kilogram, unit for v squared, m squared, v squared. Okay, so we check whether 1 Newton times meter is the same as the unit of kinetic energy. Unit for 1 Newton in SI unit. From what we learned, force equals ma, so 1 Newton should equal to 1 kilogram meter per second squared. Okay, 1 Newton, it's 1 kilogram meter per second squared times meter, which gives you kilogram meter squared per second squared. You see, the unit for kinetic energy 1/2 mv squared is also kilogram meter squared second squared, and they are exactly the same. So work and kinetic energy has the same unit. Now we're ready to introduce the work energy theorem. So in this problem, you see we have an airplane. There's a net force acting on the airplane. And initially the airplane has velocity v0. The force applied and the airplane moves a displacement of s. And its final velocity is vf. So there is a relationship between the work done by the force and the kinetic energy of the airplane. So we have the network, total work done on the airplane would be the net force times its displacement. And because force is in the same direction as displacement, the angle is 0, so cosine 0 gives us 1. That's enough. And also from Newton's second law, right? Newton's second law, we have net force equals ma s. So we have it also equals mas. Now we want to recall a very important kinematic equation. If you kind of remember 2as equals vf squared subtract v0 squared. So which gives us as in terms of vf squared and v0 squared. So we can continue. As is 1/2 vf squared subtract 1/2 v0 squared, which is nothing but 1/2 mvf squared subtract fv0 squared. So now we find the relation between the net work done on the airplane and its changing kinematic energy. So we have net force done on the airplane actually equals to its final kinetic energy. See, final kinetic subtract initial kinetic energy. So we have net force, the work done by the net force on the airplane equals to the change of kinetic energy. This is called work energy theorem. So let's use the work energy theorem to study this conceptual example. We have two satellites. One is orbiting around the Earth in a circular orbit. Another one is orbiting around the Earth in an elliptic orbit. So that's the velocity, or actually the velocity of the satellite of course change because the direction of the velocities all keep changing. I think the more accurate question is whether the speed of the satellite change for case A and case B. Now for case A, we need to find out, because change of kinetic energy equals the work done on the satellite, the net work done on the satellite. See, the satellite, there is only one force acting on the satellite, and it's always pointing to the center of the Earth. So when the satellite is somewhere here, its velocity is in this direction, displacement is tangent to the circle, but the force is perpendicular to the circle. So in case A, we have F perpendicular to displacement. So the angle between F and S is 90 degrees. So if you find out the force done by gravity, it's Fs cosine 90 degree, and cosine 90 degree is 0. So the work done by gravity is 0. So the net work done on the satellite is 0 always, no matter where the satellite is. Now from the work energy theorem, we recall work and energy theorem. Net work done on the satellite is KEF subtract KEI, change of kinetic energy. So in case A, gravity is not going to do any work on the satellite. So there's no change in kinetic energy. If there's no change in kinetic energy, there's no change in velocity. So in case A, velocity is a constant. Let's look at case B. We study these two special positions. So when the satellite moves from here to here, that's the direction of displacement. And that's the direction of gravitational force. There's an angle between them, let's say theta, and let's call it theta 1. And you see theta 1 is somewhere between 0 and 90 degrees. So the work done by gravity is positive. And what we can say is positive because you have is force times displacement times cosine theta 1, and the cosine theta 1 is positive. So the work done by gravity is positive. If the work done by gravity is positive, then from the work energy theorem, the kinetic energy of the satellite, Ke, at this location would increase at this location. Now, let's study this special location, and that's the direction of force, just the direction of displacement, angle between them, let's call it theta 2. You see theta 2 is somewhere between 90 degree and 180 degree. So the work done by gravitational force here is negative. So when the network is negative, kinetic energy will decrease. So at this location, when the satellite moves this way, its kinetic energy is going to decrease. So depends on the orbit of a satellite. Actually, its velocity is not going to change if it's a circular orbit. If it's elliptic orbit, actually the velocity of the satellite changes. And we can go more quantitative later after we learn energy conservation. Okay. Let's study one more example of the work energy theorem. So you have a block. Initially is at location A and pushed by a force to location B. The force is 2 Newton, has an angle 40 degrees with back to the horizontal direction. A and B is 1.5 meter. We know the kinetic energy of the block at position A is 5 joules. The kinetic energy at the location B is 4 joules. Want to find out how much work is done on the block by friction when the block is moving from A to B. So we use work and energy theorem. So the net work done on the block equals the change of kinetic energy. Final kinetic energy, which is kinetic energy at position B. Subtract its initial kinetic energy is kinetic energy at position A. So the net work done on the block from A to B is negative 1 joules. Now, there are only two forces doing work on the block during this motion. You have normal force, you have gravity, but you see normal force and the gravity, they all perpendicular to the displacement, which means the angle of force and displacement for normal force and gravity is 90 degree, cosine 90 degree 0. Normal force mg doesn't do any work on the block. So the net work on the block should be only from the applied force P and friction. So you need to find out what's the work done by force P, which is P times S times cosine 40 degree, and is 2.3 joules. Now we know net force is negative 1, WP is 2.3, so the work done by friction has to be net force, subtract WP is negative 3.3 joule.